So using an online tool called Desmos, I have grabbed my secant of x and its derivative, secant of x tan x. And we want to identify some of the key features on secant of x and secant x tan x. To help us do this, let's get some bearing by drawing our cos of x graph here. Okay, so we see that there's an asymptote there, and there's approximately an asymptote somewhere over here, another one over here. Okay, so the cos graph will do something like that. Okay, we see that the slope of the tangent to the secant of x is flat there. Okay, so that slope is equal to 0. And in turn, we see that our derivative, its y value, okay, or its y-intercept, is equal to 0 as well. Okay. Now, if we're to compute y prime at 0, okay, we should get an instantaneous rate of change of 0. As we move to the right of 0, as x gets bigger and bigger, okay, what do you notice happening to the instantaneous rate of changes, or the slope of the tangents? We see that they get steeper and steeper. And we see that reflected in the values, in the y value that the purple graph takes, right? As we move this way, these values get bigger and bigger and bigger and bigger. Okay. Same thing here. If we're to look at this particular value, the slope of the tangent to secant of x is equal to 0. And we see that here in the purple graph. It intersects the x-axis at 0. And as we move away from it, what do you see happening to the slope? Okay, it gets steeper and steeper and steeper, right? Or if we move to the right, it gets steeper and it gets less and less and less and less steeper, eventually reaching a slope of 0. And we see that here, right? These values are super big values, but they get smaller and smaller as we approach, as we get closer and closer to this value here, which is 3 pi over 2. Okay, eventually settling at a value of 0, okay, which tells us that the slope of the tangent, or the instantaneous rate of change when x is equal to 3 pi over 2, is a flat line or 0.